Hi guys, welcome back to our physical chemistry lecture series. So in this video, we'll be discussing a topic that's a little different from our previous discussion on thermodynamics. So this time we'll be looking at the field of chemical kinetics, which now deals with the rates of chemical processes. Okay, so just to emphasize the difference between the fields of thermodynamics and kinetics, recall that thermodynamics deals with systems in equilibrium. Okay, so all the parameters that we've studied for our systems are those that correspond to equilibrium states. And even if our system undergoes different processes, the final state will correspond to the final equilibrium state. And in addition, when we're studying these processes, we're typically interested in the changes in state functions for these processes, so we're just concerned again with the final and initial state of our system. So overall, we're not really looking at anything that happens in between, right? Like how the initial state arrives at the final state. So thermodynamics isn't really concerned with how equilibrium is reached, like how long it actually takes, or the mechanism by which it arrives at that state. Okay? And a nice example of this missing part from thermodynamics is one that some people might find to be intuitively surprising. So this is the stability of diamond versus graphite. Okay, so if we look at the standard Gibbs free energy of formation for diamond formed from graphite, we could see that the standard Gibbs free energy is positive. So this implies that the process in which diamond transforms to graphite has a negative Gibbs free energy. So therefore it is spontaneous. Okay? This ultimately tells us that diamond is actually not stable at standard conditions, and it will spontaneously transform to graphite. So of course, we could ask ourselves, why don't we see diamond breaking down into pencil lead by now? Okay? So actually, while the process is indeed spontaneous according to thermodynamics, the process takes a very, very, very long time to happen. Okay? So according to some sources, it could take like 10 raised to 80 seconds to occur, which is long enough to be forever for us. So overall, that's why thermodynamic parameters don't necessarily tell the whole story when we want to study processes of interest. After all, we also want to know practical things like how long a process can occur, and this question is addressed by kinetics, which can complete the picture for us. Okay? So chemical kinetics, this is overall the study of the rate of chemical reactions. Okay, this field addresses a number of questions like how fast are reactants consumed and products formed, what factors affect the rate of a reaction. So this will allow us to optimize reaction conditions to maximize the rate of product formation, for example. And kinetics also addresses the question of how a reaction proceeds, which may be useful for us, especially if we're interested in intermediate compounds. Okay? So here's our discussion outline. We'll start with a review of the basics on how we could express the rate of reaction with rate laws, and we'll also look at some empirical methods to determine the rate law. So after establishing our empirical rate laws, we can look at two major kinetic theories that construct models to explain how a chemical reaction occurs. So these two models, the collision theory and the transition state theory, they give us mathematical models to understand the different factors affecting reaction rates, which includes temperature. Then lastly, we'll look at reaction mechanisms and how we can determine the rate law from a reaction mechanism. And we'll also investigate special mechanisms like unimolecular reactions and radical reactions. Okay? So first and foremost, let's establish some definitions. So we'll be using the following reaction as an example for our discussion, and we'll be looking at what happens when we start with our reactants and allow our reaction to proceed with time. All right, so say that we have a single vessel and we start at time 0 with the same amounts of reactant A and B indicated here. And initially we have no product at the start as well, okay? So when we allow the reaction to proceed, we expect to see, of course, that reactant A decreases with time, same with B, because they are reacting together to form product C, which we see increases in concentration with time. Okay, so the plot that we have here is a concentration versus time plot. So if we're interested in the rates of the formation of product and the rate of consumption of reactant, our rate is essentially just the slopes or the derivatives of these curves. So the instantaneous rates of disappearance of the reactant are given by their corresponding derivatives, and the instantaneous rate of appearance of product is given by the corresponding derivative. Okay, so a derivative evaluated at a certain time t will tell us the instantaneous rate at that time. Okay, however, if we get the change in species concentration over a change in time, say that we get delta A over delta T. Okay, so say that we're doing this from time 0 to time t, this will give us the average rate over this certain time range. Okay, but derivatives will give us the rate at an exact time. Okay, but anyway, we could see here that the slope of the tangent lines at t1 will give us its corresponding instantaneous rates at t1. Okay, so note that the slopes for our reactants are negative because their concentrations are decreasing, while the slope for the product is of course positive because its amount is increasing with time. Okay, so since we want to express the rate of an overall reaction as a positive quantity, we typically express it directly as a stoichiometric rate of appearance of product. Okay, so in this case, since there is a one-to-one correspondence for the stoichiometry of the reaction and the number of moles of C, we could express the rate of the reaction as dc dt. Okay, so speaking of stoichiometry, also note that the magnitude of the slopes is different. Okay, so in some cases they're different, in some cases, however, they're equal, and we could establish these relationships between the rates based on the stoichiometry of the reaction. Okay, so for example, the rate of disappearance for B is larger than A, since for every mole of A consumed, 2 moles of B will be consumed, so the rate of consumption of B is twice than that of A. Okay. On the other hand, for every mole of A consumed, 1 mole of C is produced, so we expect the magnitudes of the rates to be equal but opposite in sign. Okay, so we could also express the rate of the reaction as the negative of the rate of disappearance of reactant A. And we could also even relate the rate of reaction to the rate of disappearance of reactant B just by considering the stoichiometry of B with respect to the reaction. Okay, so we could see that we could also express the rate of the reaction as negative 1/2 dB dt. Okay. Another point of interest in this plot is at t0, which can tell us the initial rate of the reaction, which corresponds to the rate of the reaction the instants the reactants are mixed together. Okay, but as time proceeds, of course, the instantaneous reaction rate decreases until it reaches another point of interest, which is when the concentration versus time curves reach constant values. Okay, so there appears to be no change in concentration of species in the system here. Okay, so this pretty much is the point when equilibrium is established. Okay, so usually this happens after a significant amount of time has elapsed after mixing the reactants together, and to be super safe, the time at which equilibrium is established is generally set at infinity, okay, which usually just means a very, very long time. Okay, so anyway, if we look at the rate of reaction at this time, we can see here that the slopes of the curves, they're all equal to 0. Okay, so of course, this pretty much means that the rate of the reaction is pretty much 0. Okay, so an overall 0 rate of reaction, however, doesn't really mean that nothing is happening anymore. It just tells us that the concentration of species in equilibrium is constant. Okay, so equilibrium, after all, is actually a dynamic process, and what happens at equilibrium is that the rate of the forward reaction is equal to the rate of the backward reaction. Okay, so we see no net change in the concentration of our species at equilibrium. But of course, when we're studying kinetics, we're mostly interested in this part over here when we do see changes in the concentration of our species with time. Okay? So the next question is, how can we determine an expression of the function that describes the rate of the reaction? Okay? So from this plot, we see that the rate changes as the reaction proceeds, right? Because as the reaction proceeds, the amount of reactant decreases since it gets consumed. So naturally, it will lead to less product being formed. Okay, so we expect then that the rate of the reaction is dependent on the concentration of reactant present in our reaction vessel. Okay, so this expectation is confirmed empirically in that the rate of the reaction is usually proportional to the molar concentration of reactant raised to a power. Okay, so this can lead us to construct a function that tells us the effect of reactant concentration on rate. Okay, so this mathematical expression that relates the molar concentration of reactants to the overall rate is the rate law. Okay, so for example, if we're given a reaction A plus 2B yielding C, the rate law can be written in the following general manner. Okay, so we have rate is equal to some constant K times the concentration of A raised to M times the concentration of B raised to N. Okay, so again, our K, this is our rate constant. M is the order of reaction with respect to A, and N is the order of the reaction with respect to B. Okay, so note that the orders M and N, they need not be equivalent to the stoichiometric coefficients in the balanced chemical equation. So we'll discuss further why this is and in which special cases where the order is actually equivalent to the stoichiometric coefficients later on when we discuss reaction mechanisms, okay? But typically, these orders here, they are determined experimentally, and they could also be a very rich source of information as it can be used later on to deduce the mechanism by which the reaction occurs, okay? So as another note, guys, also keep in mind that the rate law can also include other species like catalysts and even products for more complex reactions, okay? But for simple reactions, the rate law usually shows dependence only on reactants, okay? So there are two major methods to experimentally determine the rate law of a reaction, both of which have probably been discussed in your general chemistry classes, but we'll be reviewing them here in our discussion, okay? So there are a number of advanced techniques to study reaction rates, like relaxation methods, but we'll be limiting our discussion to these two here. But overall, the method used depends on the type of data gathered, of course. So we just have to be wary of the data available to us, since I see a lot of confusion with students sometimes on which method to use when confronted with a set of data. Okay, so the first method is the most commonly encountered one, which is the isolation method. So this is also known as the method of initial rates or the differential method, but they're all pretty much based on the same principles. Okay, so the type of experimental data used here is the measurement of reaction rate. Okay, so typically the initial rate upon varying the initial concentration of reactant. Okay, so the initial rate is measured because this is the rate that corresponds to the state when we have the initial concentration of reactant, which we can easily control. Okay, so if we have multiple reactants, it would be necessary to keep the others constant while just varying one to make sure that the effect on the reaction rate is only due to the variation of that one reactant. Okay, so for example, if you want to study the following reaction here, one experimental trial might set the initial concentration of A as 1 molar, while that for B is 1 molar, okay? So another trial might increase A while keeping B constant, and we could also do another trial over here, okay? So the same procedure can be repeated for reactant B, and here's a typical set of data that we might gather for this type of experiment, okay? So for the trials in which we kept B constant while varying A, these can be used to determine the order of reaction with respect to A. Okay, so keep in mind that we have several data points over here, so it's going to be useful to plot the data in order to determine our unknown, okay? But as is, our rate law isn't very friendly in terms of plotting, so it's usually best to sort of linearize this equation in order to work with something a little bit more friendly and plottable, okay? So one strategy for this, since we're dealing with our unknown variables as an exponent, is to get the logarithm of this expression, okay? So this will give us log rate is equal to log k times the concentration of A raised to m times the concentration of B raised to n, okay? So we'll be using the rules of logarithms in order to simplify our expression. So we'll get log rate is equal to, okay, so let's put together the terms that are constant, okay? So in this case, since we kept B constant, this term over here is going to be constant as well as our rate constant, okay? So we'll have log k times the concentration of B raised to n plus the log of A raised to m, okay? So we could also use the laws of logarithms in order to bring down this exponent over here. So our final expression is going to be log rate is equal to log times our collection of constant terms over here plus m times the log of the concentration of A. Alright, so this expression here can be plotted, okay? So our x variable is going to be the log of the concentration of A, okay? So this is the parameter that we're varying in our experiment, our independent variable, and our dependent variable is the rate over here, okay? So this is set as our y variable, okay? So of course our m, the order of the reaction with respect to A, this is going to be our slope, and this part over here, our constant terms, this is going to be equal to our y-intercept, okay? So we'll be performing some linear regression in order to determine our unknown parameter, which is our slope, okay? So overall, we could plot our data. We could get the log of the concentration of A and then the log of the rate, and we could determine the order of the reaction by getting the slope, okay? So this here is the plot of log rate versus log A. And we can see here that the slope is given by this value over here. It's not going to be a perfect integer, so we might need to do some rounding. So we can see here that this value is very close to 2, okay? So we can say here that the order of the reaction with respect to A is equal to 2, okay? So the same treatment can be done for reactant B, okay? So in this case, we'll be using trials 1, 4, and 3, okay? So note that the concentration of A is held constant, okay? So these are the trials that we could use to determine the order with respect to reactant B, okay? So overall, the equation that we'll be using is going to be similar in form to the one that we used for reactant A, okay? So in this case, however, our concentration of A is going to be held constant, so our working equation is going to be the log rate is equal to the log of our collection of constant terms, so that is our rate constant, times the concentration of A raised to its corresponding order, plus n times log concentration B. Okay, so again, since we're varying the concentration of B, okay, so this serves as our independent variable x. Okay, so our rate is our dependent variable y. Okay, so our n, the order of our reaction with respect to B, this is expected to be our slope. And this term over here, this is expected to be our intercept. Okay, so we could get the log of the concentration of B and the log of the rate. And if we plot this, we see that we get this curve over here with very poor linearity. But overall, we could see here that the slope of our curve is very close to 0, okay? So we can see from the data, after all, that there's not really much of an effect on changing the concentration of B on the rate of the reaction, okay? So these variations in our values here might just be due to experimental error, okay? So we could see here that the order of the reaction with respect to B is equal to 0, okay? So we could complete our rate law, okay? So we could say that the rate of our reaction is equal to K times the concentration of A raised to 2, okay, times the concentration of B raised to 0, okay? So just for simplification, we could just say that this is equal to 1, okay? So the rate of our reaction is equal to K times the concentration of A squared, okay? So we could also solve for a value of K, okay, so using some of the trials over here, okay, so let's say that we use trial 1, okay, so solving for K, this will be rate divided by the concentration of A squared, okay, so this is just equal to 0.0101 molar per second over 1 molar squared, okay? So we can see here that K, okay, this is going to be equal to 0.0101 1 over molar second, okay? So note that the units of the rate constant will be dependent on the order of the reaction, okay? So we could use the units of the rate constant as a hint as to what the overall order of the reaction is, okay? So an alternative approach to rate law determination is a curve fitting method using integrated rate laws, okay? So the experimental data obtained for this method is the concentration of a species with time, okay? So for this particular case, we have a single reactant decomposing to form products, okay? So we start with an initial amount of reactant A at time 0, and we allow the reaction to proceed, and at regular time intervals, we can then monitor the concentration of reactant, okay? So this can be done in real time by measuring a property like absorbance as the reaction proceeds, okay? So we can actually fit all these data points together to form a smooth curve, and the function that describes this curve can ultimately tell us the rate law of the reaction, okay? So working backwards, we know that the rate of the reaction can be expressed as a negative of dA dt, which is also equal to K times the concentration of A raised to some power n. Okay, so if we integrate this rate expression, we get a function of A versus time, which is this function over here. Okay, so this function that we get from the rate is called the integrated rate law expression. Okay, so the overall objective of these types of experiments is to fit the concentration of A versus time data to an integrated rate law. Okay, so it might be necessary to try fitting it to several equations before finding the best fit. Okay, so it's kind of like a guess and check sort of thing. Okay, but of course the disadvantage to this is that you need to have worked out the integrated rate law expression, which can really get complicated if we deal with more than one type of reactant. So that's why for our discussion, we'll be limiting ourselves to just one reactant type reactions. Okay, so again, here we have our general expression for the rate law with an order of n. Okay, so for every value of n, actually, there will be a unique integrated rate law expression. Okay, so let's evaluate the integrated rate law expressions for commonly encountered orders, starting with the 0th order. Okay, so let's write down the rate expression for this. Okay, so this will be negative dA over dt. This is equal to K times the concentration of A raised to 0, okay? So this term over here actually simplifies to just 1, so our expression just becomes negative dA over dt is equal to K, okay? So we have this differential equation over here, so it's going to be useful if we transfer this differential to the other side, okay? So we'll have dA is equal to K negative K dt. Okay, so we could integrate this expression. Okay, so we'll be integrating from time 0 to a certain time t. Okay, so this corresponds to the concentration of A, the initial concentration, to the concentration of A at a certain time t. Okay, we'll be evaluating this from 0 to t. Okay, so the integration for this is straightforward. Okay, so the integral for dA is just going to be A. Okay, so our expression just becomes concentration of A at time t minus the concentration of A at the initial is equal to negative KT. Okay, so it's t minus 0, all right? So we could arrange this equation. Okay, so we have concentration of A at time t is equal to negative KT plus the initial concentration of A. All right. Okay, so if we arrange our equation in this following way, okay, we could definitely see here that we have a concentration versus time curve. Okay, so our graphical test, in order to check if the order of our reaction is equal to 0, is that we could plot time on our x-axis. Okay, so this is going to be our x variable. Okay, and then our y variable is just going to be concentration. So if our reaction is indeed 0th order, we expect that we're going to get a linear curve. Okay, so the corresponding slope is going to be the rate constant. Okay, and then the initial concentration of A is expected to be our intercept. Okay, so again, we plot T on our x-axis, and then we have the concentration of A. Okay, so we expect that we're going to get a negatively sloping curve like this here. Okay, so the slope here, this is going to be equal to negative K, and of course, the concentration at time 0, this is expected to be the concentration of A at the initial state. Okay, so we'll be doing some linear regression here to check if the data does indeed fit this linear curve over here, so we could evaluate the r squared of the data when we fit it in this type of form here. Okay, so note again, guys, that we usually do linear regression since it's a simple type of curve fitting that we could perform. So an easy way to evaluate whether the expression fits our linear equation is just by checking the Pearson coefficient squared. Okay, so we could also derive an integrated rate law for other orders. Okay, so let's check out what happens if we want to check if the order of the reaction is equal to 1. Okay, so starting again with this same basic equation over here, we could write negative dA over dt is equal to K times the concentration of A. Okay, so the order of the reaction is equal to 1. Okay, so let's rearrange our expression. Let's bring all the terms that contain the concentration of A on one side and then separate the differential over here that contains T on the other side. So we have dA over the concentration of A is equal to negative K dt. So our expression over here, we can now integrate this with respect to each variable. Okay, so we'll be integrating this side from the initial concentration to the concentration of A at time t. And on this side, we'll be integrating from 0 times 0 to the time of interest. Okay, so upon evaluating this, note that dA over A, this gives us ln, okay, the natural logarithm. So our expression here becomes ln of the concentration of A at time t minus ln of the concentration of A at time 0 is equal to, again, negative kt. So we could again rearrange this expression. Okay, so we'll get ln of the concentration of A is equal to negative kt plus ln of the initial concentration. Okay, so again, if we write our expression in this form over here, we could see here that we have a linear equation. Okay, if we set time t as x, and then the ln of our concentration of A as our y variable. Okay, so if we plot these variables here, our slope is expected to be our negative k, and our intercept is expected to be ln of the initial concentration. Okay, so if we plot this over here, we plot t on the x-axis, ln A over here on the y-axis, we'll get a negatively sloping curve with negative k as a slope, ln of the concentration of A at the initial state as our intercept. Okay, so again, to check if our reaction is indeed first order, check the value of r squared. Okay, so next we could check if our reaction is second order. Okay, so again, same exact procedure. Okay, so let's start with our basic expression over here. Okay, so we have dA dt is equal to K times the concentration of A squared. Okay, so again, let's rearrange our expression over here. Let's separate our differentials. Okay, we'll get dA over A squared is equal to negative kt. Okay, so we'll be evaluating at the same limits. Okay, so initial concentration of A to the concentration of A at time t. Okay, 0 time to time t. Okay, So upon evaluating this, we expect to get negative 1 over the concentration of A at time t minus the negative of 1 over the initial concentration is equal to negative kt. Okay, so we could rearrange and simplify this expression. So this will be 1 over the concentration of A at time t is equal to kt plus 1 over the initial concentration. Okay, so if we write our expression in this following way, we could see here that if we set our time as our x variable and the inverse of our concentration as our y variable, our slope is going to be the rate constant k, and our intercept is going to be the inverse of our initial concentration. So the graphical test to check if our reaction is indeed second order is to plot time on our x-axis, the inverse of the concentration on our y-axis, and we'll expect to get a positively sloping curve in which the slope is equal to k, and the intercept here is equal to 1 over the initial concentration of A. Alright, so again, we'll have to check the r squared to check the linearity of our curve here. Okay, so again, usually we'll have to check several integrated rate laws and compare the corresponding linearity or the fit of our data to these linearized integrated rate laws. Okay, so another important parameter that can be derived from the integrated rate law is half-life. Okay, so this is just the time it takes to have the initial concentration of reactant. Okay, so based on this definition, at the half-life, the concentration of A is just going to be half of the initial concentration. Okay, so using this definition, we can derive expressions for the half-life of a reaction based on the integrated rate law expressions. Okay, so if our reaction is 0th order, so let's check out what our expression for half-life is going to be. So let's recall our integrated rate law expression. So that is just AT is equal to negative KT plus the concentration of A at the initial state. Okay, so again, we'll be using this definition over here. Okay, so we could replace the concentration of A as 1/2 times the initial concentration is equal to negative KT half-life plus the concentration of A at the initial state. Okay, so solving for the half-life, okay, so the half-life, this is going to be equal to, okay, so this is going to be negative 1/2 of the initial concentration over negative K. Okay, so this simplifies to the half-life for a 0th order reaction is going to be the initial concentration over 2K. Alright, okay, so we could see here that the half-life is directly proportional to the initial concentration. Okay, so if we look at consecutive half-lives, okay, so for example, let's say that we start at an initial concentration of A, okay, and then we proceed to half of the initial concentration. Okay, so this is going to be our first half-life. Okay, so if we now use this as our initial concentration, how much time is it going to take to have this concentration? So in other words, how long is it going to take to get to 1/4 of the initial concentration of A? Okay, so that is going to be our second half-life. Okay, so based on this, since we decrease the initial concentration, we could see here that we decrease our half-life as well. Okay, so it's going to take a shorter time to decompose this existing amount of A. Okay, so we have 1/4 of the initial concentration of A over here, and we continuously expect this to decrease for consecutive half-lives. Okay, so now let's look at what happens when the order of a reaction is equal to 1. Okay, so again, let's recall the integrated rate law expression for this. Okay, so we know that this is the ln of the concentration of A at time t is equal to negative kt plus the ln of the initial concentration. Okay, so setting our time as the half-life, okay, so we could rewrite this expression for the concentration of A at time t as 1/2 of the initial concentration is equal to negative kt half-life plus ln of the initial concentration. Okay, So rearranging this, okay, we get ln 1/2 initial concentration of A minus ln initial concentration is equal to negative kT half. Okay, so we could use the rules of logarithms, okay, and we could express this as ln 1/2 initial concentration of A over initial concentration of A. Okay, so we could see here that this cancels out. So this is equal to negative kT half-life. Okay, so we have ln 1/2 is equal to negative k half-life. Okay, so note that we could express 1/2 as equal to 2 raised to negative 1, right? Okay, so let's rewrite this expression over here as ln 2 raised to negative 1. Okay, so this is equal to negative kT half-life. Okay, so using again the rules of logarithms, we know that we could bring down the exponent here as a coefficient. Okay, so we could rewrite this as negative ln 2 is equal to negative kT half-life. Okay, so this ultimately simplifies to the half-life of a first order reaction is just equal to ln 2 over k. Alright, okay, so the important thing to note here is that the initial concentration of A does not appear in our expression. Okay, so this tells us that the half-life of our reaction is independent of the initial concentration. Okay, so if we look at consecutive half-lives, so say again that we start at an initial concentration of A, and then we want to have this, okay, so this is going to take 1 half-life, right? Okay, so if we want to have this value over here, we could see here that our half-life for a first order reaction is independent of initial concentration, right? So it's actually going to take an equal amount of time to get to 1/4 of the initial concentration of A. Okay, so same half-life, okay, so this will also take the same amount of time to get to 1/8 of the initial concentration. Okay, so all of these values here of our half-life are equal. Okay, so it shows no dependence on the initial concentration of A, and it's just dependent on the rate constant here. Okay, so we could also do again the same treatment for our second order reaction. Okay, so let's recall our expression for the integrated rate law. So this is 1 over the concentration of A at time t is equal to kT plus 1 over the initial concentration of A. All right, so setting our substitutions over here. Okay, so the concentration of A at the half-life is going to be 1/2 of the initial concentration. So this is going to be equal to K times the half-life plus 1 over the initial concentration. Okay, so rearranging this expression and solving for the half-life, okay, so note that we have a fraction in the denominator over here, so we could raise this up into the numerator. So we have 2 over the initial concentration of A minus 1 over the initial concentration is equal to K times the half-life. Okay, so just solving for the half-life then, okay, so we get 1 over the initial concentration of A times the rate constant here. Okay, so this is our expression for the half-life of a reaction if the order of a reaction is equal to 2. All right, okay, so we can see here that in contrast to our 0th and our first order reactions, the half-life is now inversely proportional to the initial concentration. Okay, so this tells us that if we're looking at consecutive half-lives, we expect that the half-life is going to be increasing if we decrease the concentration of our initial concentration of A. Okay, so again, if we start with an initial concentration of A, okay, so this is going to be our first half-life. Okay, so the second half-life, in order to get 1/4 of the concentration of A, okay, from here, this is going to take a much longer time. Okay, so this is 1/4 of the initial concentration of A. So the second half-life is going to be longer than the initial half-life. Okay, so just to summarize, okay, so for 0th order, our integrated rate law is as follows. Okay, so we could plot the concentration of A versus time in order to test if we have a zeroth order reaction. And the half-life expression is as follows. Okay, so we could see here that we have a direct relationship between the initial concentration of A and the half-life. Okay, so for first order, okay, the integrated rate law is as follows. Okay, so we need to plot ln of the concentration of A versus time in order to test whether our data fits first order. And the half-life of our expression is shown to be independent of the initial concentration of A. All right, so we expect to have constant half-lives as our reactant breaks down. Okay. In addition, for second order, okay, so this is our integrated rate expression, so we should be plotting the reciprocal of our concentration of A versus time in order to evaluate whether our reaction is second order. And we can see here that the half-life is inversely proportional this time to the initial concentration of A. Okay, so with all this in mind, let's try to solve a couple of problems using integrated rate laws. Okay, so first, let's check out this problem over here. Okay, so we're dealing with changes in blood plasma concentration of a beta blocker drug with time. Okay, so we pretty much have a one reactant type process, and we want to determine if the drug removal is a first or second order process. Okay, so luckily, we just need to check if our concentration versus time data fits the first or second order integrated rate law expressions. Okay, so to check if our data fits the first order integrated rate law, we'll just need to plot the natural log of concentration versus time. And to check if it fits second order, we'll need to plot the inverse of concentration with time. Okay, so plotting our data and getting the linear regression curves, we see that our data fits the first order integrated rate expression more. Okay, so we can see that from the Pearson coefficient squared. Okay, so the R squared value over here is 0.9984. Okay, so we have very good linearity here. But over here, we see that our data points are kind of curving here, so it doesn't really fit our second order integrated rate expression as much. Okay, so overall, we could conclude that the rate of the process is first order. Okay, so we could write the rate of drug removal as rate is equal to K times C. Okay, so C in this case is the drug concentration measured at time t. All right, so we can determine the rate constant from our plot over here. Okay, so recall again that our integrated rate expression is ln C in this case is equal to negative KT plus ln C naught. Okay, so we can see here that the slope corresponds to the negative of the rate constant. Okay, so that means that K, this is equal to 0.0076. Okay, so be sure to include units. Okay, so our units for time is in terms of minutes. Okay, so that means our rate is in terms of concentration per minute. Okay, so C, this is our concentration. So that means that K, this has to be in terms of 1/minute. Okay, so this is our rate constant over here. Okay, so next we want to determine the half-life of the process. Okay, so since we know that our reaction is first order, we could use the expression for the first order half-life, which is equal to ln2 over K to determine the half-life of this process. Okay, so this is ln2 over 0.0076 inverse minutes. Okay, so that means the half-life of this process is 91.2 minutes. Okay, so next up, let's try out this problem over here, which requires a little bit more analysis. Okay, so at 60 degrees Celsius, we're given the following reaction, which we know to be first order, and we also know that it proceeds to completion. Okay, so when we have pure A decomposing in an empty vessel, we are given the total pressure at 10 minutes and also the total pressure after a very long time. Okay, so we're tasked to calculate the initial pressure of A after 10 minutes, the rate constant, and the half-life of the reaction. Okay, so note here that in this problem we're given pressures. Okay, so previously when we're dealing with rate constants and whatnot, we were dealing with concentration. Okay, but note that we could assume that we have ideal gas behavior for our gaseous system, and from the ideal gas equation we know that it's PV is equal to nRT, right? So we could rewrite this as pressure is equal to N over V times RT. So N over V, this is just our concentration. So we know that our pressures are directly proportional to our concentrations. Okay, so in place of concentrations, we could just use partial pressures of each of our components. Okay, an additional important note about this problem is that the given information is total pressure. Okay, so that means the total pressure, this is equal to the corresponding partial pressures of our reactants and our products all at the given times. Okay, so that means we also need to keep in mind what happens to our amounts of both the reactants and the products as the reaction proceeds. Okay, but luckily we know that we start out our reaction with only pure A in an empty vessel. Okay, and we're also given the stoichiometry of the reaction anyway. Okay, so it's very useful in this particular problem to kind of write out a reaction table. Okay, so we want to see what happens at 10 minutes and also after this very long time over here. Okay, so let's check out what happens. Okay, so let's write down our reaction. We have A, okay, decomposing into B plus 2C. Okay, so let's indicate what we have in the initial state. Okay, let's also indicate our changes. Okay, so this kind of looks like an ice table, right? But instead at equilibrium, our final state will be at time of 10 minutes and also at time when we have a very long time, or T infinity. Okay, so our initial state over here, okay, we have pure A. So let's say that this is the initial pressure of A. All right, we only have A in our vessel initially, so we have 0, 0. Okay, so our reaction will proceed as follows. Okay, so for every mole of A, okay, there's going to be 1 mole of B that forms, okay, and then 2 moles of C that form. Okay, so we could express the partial pressure of A at time 10 minutes as the initial pressure of A minus X. Okay, so the partial pressure at 10 minutes for B is going to be X, and for C it's going to be plus 2X. Okay, so as for time infinity, the expressions over here are actually going to be the same, but let's just indicate the corresponding changes with a prime. Okay, so we have initial pressure of A minus X prime. Okay, the partial pressure of B is going to be X prime, and then the partial pressure of C is going to be 2X prime. Okay, so in general, we could also write down an expression for our total pressure. Okay, so the total pressure is just going to be the summation of all the partial pressures, right? Okay, so the partial pressure of A at any time T. Okay, so let's indicate this, that this is the expression for the total pressure at any time T. This is the partial pressure of A, so that is initial pressure minus X plus X. Okay, so this is the partial pressure of B plus 2X. Okay, so we can see here that this expression simplifies out to PA naught plus 2X. Okay, so again, in this particular problem, we're just given the total pressure after a certain time T. Okay, so we don't know what this is yet. Okay, but a big hint to this problem in determining the initial pressure of A is this date over here. Okay, so what exactly happens after a very long time? Okay, so initially we kind of mentioned this whole time infinity over here, right? So this is when we have equilibrium established. Okay, but in this particular problem, we know that the reaction proceeds to completion. Okay, so this implies that after a very long time, our reactant A gets completely consumed. Okay, so we know that after a very long time, this quantity over here, the partial pressure of A, is expected to be 0. Okay, all right, so let's move on to a fresh slide just to get more space over here. Okay, so again, just to emphasize, at T approaching infinity, okay, so we know that the partial pressure of A, okay, this is expected to be 0, right? Because our A gets completely consumed, okay? So the reaction proceeds to completion, okay? So the partial pressure of A is given as PA naught minus X prime, okay? So this allows us to express the initial pressure of A as X prime. Okay, so let's recall our expression for the total pressure, okay, at time infinity. Okay, so this is going to be equal to the initial pressure of A plus 2x prime, okay? So from our analysis over here, we were able to express the initial pressure of A as x prime, okay? So this gives us Pt infinity is equal to, okay, so this is x prime, so this is equal to 3x prime, okay? So we know the total pressure at a very long time, right? So that is equal to 270 torr, okay? So 270 torr, that is equal to 3x prime. Okay, so that means that the corresponding change at a very long time is going to be equal to 90 torr. Okay, so since we know that x prime, this is equal to the initial pressure of A, okay, so that means that the initial pressure of A, this is equal to 90 torr. Okay, so overall here, we solved this problem here now, okay? So next we want to solve for the pressure of A after 10 minutes, okay? So our expression for the total pressure at 10 minutes, okay? So this is going to involve a different change now, okay? So this is going to be PA naught plus 2x, okay? So now we can determine what the change was at 10 minutes, okay? Inputting all our values over here. So we know that the total pressure at 10 minutes was 170 torr, okay? The initial pressure of A is 90 torr, okay? So solving for x, this will be equal to 40 torr. All right? Okay, so we could write the partial pressure of A at 10 minutes as the initial pressure of A minus x. Okay, so we already know what this is, right? So this is 90 torr, and we know that x is equal to 40 torr. So the pressure of A after 10 minutes, we could say that this is 50 torr, right? Okay, so next up, we need to determine the rate constant and the half-life of the reaction, okay? So we already know that the reaction is first order, so it's just a matter of applying the first order integrated rate law expression, okay? So let's move on to the next slide. Okay, so our rate law expression, as we solved earlier, was ln of the concentration of A at time t is equal to negative kt plus ln initial concentration, okay? So we could adapt this for pressures by writing instead ln of the pressure of A at time t is equal to negative kt plus the ln of the initial pressure of A, all right? Okay, so let's just rearrange this. Okay, so actually we just have two data points that we know. Okay, so we know that at time 0, the initial time, okay, so we know the initial pressure, right? So the initial pressure of A is equal to 90 torr, right? And then at 10 minutes, we also know that the pressure of A at 10 minutes is equal to 50 torr. Okay, so we could just use like a two-point form of the integrated rate expression, okay? So solving now for the rate constant, okay, so we could rearrange this expression, okay? So we'll get ln PA, partial pressure of A at time t, over the initial pressure. This is equal to negative kt, okay? So overall, the rate constant is going to be equal to negative ln of the partial pressure of A at time t over the initial pressure divided by the time. Okay, so K, this is equal to negative ln 50 torr over 90 torr over 10 minutes. Okay, so our rate constant, this is equal to 0.0588 reciprocal minutes. All right. Okay, so next, let's solve for the half-life. Okay, so we know that the half-life expression is just equal to ln2 over k. This gives us 11.8 minutes. Right, so this is the half-life. Okay, so overall, we are now familiar with experimentally determining rate laws, okay? Of course, keep in mind that we've arrived at these descriptions of the rate of a reaction empirically, and currently we have no insight as to what happens exactly on a molecular basis, okay? So in other words, while we can describe and predict the rate of a reaction, we don't exactly have a picture yet of why the rate law is the way it is and why the rate constant for a certain reaction is the way it is, okay? So what we need now is a model that could explain reaction rates, okay? And hopefully by the end of our discussion of these two major chemical kinetic theories, collision theory and transition state theory, we could answer the following questions. Okay, so 1, how does a reaction occur? And 2, what is the meaning of the rate constant? Okay, so the first and simpler theory we'll be discussing is collision theory. Okay, so this theory pictures a chemical reaction as a collision between the reactants. Okay, so more specifically, a collision with both the minimum kinetic energy and orientation that can facilitate bond breaking and bond making for the formation of products. Okay, so for example, if two reactants collide, but it doesn't have enough kinetic energy, there will be no reaction. Okay, but if the reactants collide with sufficient energy and also proper orientation, it is possible to form products. So this type of collision is called an effective collision, okay? So an additional note about collision theory, guys, is that collision theory is modeled after ideal gas behavior, okay? And imagines molecules to be hard, rigid billiard balls as pictured here. So in our discussion, we'll be using many of the equations that we derived from our earlier discussion on ideal gases and the kinetic molecular theory, including collision frequency and the Maxwell-Boltzmann distribution. Okay, so the energetics involved in an effective collision can be visualized using an energy reaction coordinate plot here. Okay, so if we start with our energy of our reactants here, okay, the two reactants can collide with sufficient energy going over this energy barrier here to form products. Okay, so the energy barrier, the energy required for an effective collision, is just the activation energy. Okay, so overall, based on collision theory, we could see that the rate of formation of products and ultimately the overall rate of the reaction is dependent on the number of effective collisions that can occur. Okay, because as soon as there is an effective collision, products will then soon form. Okay, so again, the reaction rate is directly proportional to the number of effective collisions. Okay, in turn, the number of effective collisions will be directly proportional to the collision density, which, recall, is a number of collisions per unit volume per unit time. Okay, but note that not all collisions will result in a reaction. Okay, so the number of effective collisions will also be dependent on the fraction of molecules with the minimum energy requirement. So far then, our overall reaction rate will be proportional to the collision density times the fraction of molecules with the necessary activation energy. Okay, so finally, we could also add another constant here, rho, to account for additional orientation requirements for an effective collision. Okay, so rho is also known as the steric factor, and it's usually determined experimentally as a correction factor from the ideal symmetric effective collision. Okay, so let's just go over each of these terms and expand them. Okay, so first, the fraction of molecules with the minimum required energy can be derived from the Maxwell-Boltzmann distribution curves. Okay, so recall again that these curves are a function of temperature. Okay, so the higher the temperature, the more molecules there are in higher energy states. Okay, so as illustrated in this figure, the minimum speed here corresponds to a minimum kinetic energy for our molecules to have an effective collision. Okay, so this corresponds to the speed required for the activation energy. Okay, so areas under these curves correspond to the fraction of molecules that have this speed or greater. Okay, so we can see here that at higher temperatures, there is a greater shaded area over here compared to that in the lower temperatures. Okay, so the expression for the fraction of molecules with this minimum energy is just given as follows. Okay, so F is equal to E raised to the negative activation energy over RT. All right, so next we could recall the expression for collision density. Okay, so collision density is given as follows. Okay, so we have the concentration of reactant A in molecules per volume times the concentration of B in molecules per volume times the collision area times the average velocity, okay? So we'll just modify expression a bit so that we could express the concentration in terms of molarity instead, okay? So since we have number of molecules up here, we can convert this to moles by dividing by Avogadro's number, okay? So for the entire equation, we'll need to multiply it by Avogadro's number squared over Avogadro's number squared, okay? So this is just a form of 1, okay? So we can convert the number of molecules over here each to number of moles of reactant, okay? So we now have over here number of moles of reactant A over volume times the number of moles of reactant B per volume, okay? And our additional Avogadro's number squared is over here, okay? So now we have the expression for concentration in terms of molarity now for both A and B. Right, so putting all our terms together, we now have the following expressions. Okay, so let's just rearrange this expression. Let's take out the concentration of A and B out here. Now we could see how we have this large collection of terms that will be constant for our system at set conditions. Okay, and this entire expression here is pretty much the rate constant K. So rewriting this expression here as K, we pretty much just have our expression for our empirical rate law now, okay? So note, we now have an interpretation for the rate constant K, and we can see that it considers activation energy and orientation requirements for an effective collision, okay? But note, however, that the expression for K was derived using ideal gas behavior and approximations, so collision theory is a rather simplistic model that applies mostly to gas systems, okay? But we can still conclude many things from here. So for one, we could see the effect of activation energy in the reaction rate. Okay, so higher activation energies implies lower rate constants and therefore slower reactions. So for example, the reason why the decomposition of diamond to graphite takes such a long time is due to the very, very high activation energy necessary, okay? In addition, from our reaction model, we can pretty much see that any factor that would lead to an increase in the chance for an effective collision will pretty much lead to an increase in rate, like increasing the concentration and also increasing the surface area of solid reactants, okay? But these generalizations, of course, are for simple one-step, one-collision reactions, okay? So when we look at more complex reactions, there may be other effects with regards to changing the concentration of reactants, okay? But nonetheless, the collision theory model gives us a nice, intuitive, simple picture of chemical reactions, okay? On the other hand, a more sophisticated model that has greater applicability in gaseous and even aqueous systems is the transition state theory, also known as the activated complex theory. Okay, so this model imagines chemical reactions occurring when reactants approach each other, causing their potential energies to increase until they distort and form this activated complex over here. Okay, so this unstable high energy complex, also known as the transition state, is a fleeting arrangement of atoms in which there are both bonds being partially broken and bonds being partially formed, okay? However, once this activated complex forms, it could either pass to form products or it could revert back to the reactants, okay? So this model is very similar to collision theory in that there is an energy barrier, but transition state theory is more detailed on what happens exactly at the top of the energy barrier. And it also notes that the formation of the activated complex does not necessarily mean that it immediately proceeds to form products, okay? So the analysis of the transition state is a little more complex, but overall we look at the probability of the transition state passing to the products in determining the overall rate of the reaction. Okay, so this includes the analysis of the equilibrium established of the reactants forming the activated complex, noted here by the double cross symbol. So this equilibrium has its own equilibrium constant K. Okay, so the formation of the activated complex constitutes when the reactants reach the energy barrier. Okay, so once the reactants form the transition state, the rate of successful passage is related to the overall rate constant K by the so-called A-ring equation given below. Okay, so this is where K, the rate constant, is equal to kappa, the transmission coefficient, which is related to the probability of passing to the products, times Boltzmann's constant times temperature over Planck's constant, and times the equilibrium constant over here. Okay, so actually it's a little bit more informative to write K as delta G instead. So we could express the equilibrium constant K as e raised to negative delta G over RT. Okay, and we could express delta G in terms of the enthalpy and the entropy. Okay, so this is written as negative delta H minus T delta S, okay, over RT. Okay, so using properties of exponentials, okay, so we could separate this term over here as e raised to delta S over R times e raised to delta H over RT, right? Okay, so we could input this expression into our expression for our rate constant. Okay, so let's just rewrite our Eyring equation in this form over here. Okay, so analyzing the Eyring equation now, okay, we could see here that this term contains the activation energy requirement, okay, because the enthalpy of the transition state, this corresponds to the activation energy, okay. In addition, the requirement for a special orientation for the transition state is contained in our entropy term over here, okay. So we expect that entropy is going to be more negative, suggesting greater order, if we have stricter orientation requirements for the transition state, okay. So putting all these terms together into our rate law, okay, so we have rate is equal to our Eyring expression over here times the corresponding concentration of our reactants. So overall, the equations that we derive from both the collision theory and transition state theory can give us equivalent insights on the effect of temperature on reaction rates, okay? So from the general rate expression, K can be expanded, okay? So from the collision theory, K can be expanded as follows, and from the transition state theory, K can be expanded as follows as well, okay? So note that there are nice similarities between the two expressions for K. So we have the following parts that take into account the orientation requirements for reaction. So in the case of collision theory, we have rho, and in the case for the transition state theory, we have our delta S over here, okay? And we also have this common exponential term over here, which takes into account the energy requirement for a reaction, right? So to simplify these expressions, the temperature effects are mostly pronounced with this exponential term over here compared to the other terms. Okay, so we can treat the other terms to be constant with temperature, and we could rewrite our expression for K as just a constant, times e raised to negative EA over RT. So this is known as our Arrhenius equation, and the constant A over here is simply known as the pre-exponential term, all right? So this equation pretty much tells us the effect of temperature on the rate of reaction and also its relationship with the activation energy, okay? So recall that this is related to the Maxwell-Boltzmann distribution, and we could see that as we have higher temperatures, there's a greater fraction of molecules which have the necessary activation energy, and this translates to greater reaction rates, right? So a major application of the Arrhenius equation is to determine the activation energy of a reaction or to determine the rate constant at different temperatures, okay? So one method of analyzing this is to measure the rate constants at different temperatures to get a linear equation, okay? So the Arrhenius equation can be linearized by getting the natural log of both sides of the equation. Okay, so we get ln k is equal to ln of our expression over here. So using the laws of logarithms, we could separate and simplify this expression to ln k is equal to ln a minus ea over r times 1 over t. All right, so what we could plot here is our temperature as our independent variable and our rate constant, the natural logarithm of our rate constant, as our dependent variable y. Alright, so if we plot these two things together, our expected slope is going to be negative EA over R, and our intercept is expected to be our ln of the pre-exponential factor. So again, if we plot ln of our rate constant versus 1 over temperature, we expect to get a negatively sloping curve with negative EA over R as our slope and our intercept as LNA. Okay, so let's apply the Arrhenius equation for this problem over here. Okay, so we're given the rate constants for the decomposition of dinitrogen pentoxide at various temperatures, and we want to calculate the activation energy of the reaction. Okay, so our given temperatures over here are in degrees Celsius, so it's important that before we proceed that we convert this all to Kelvin, all right? Okay, so recall again that the linearized form of our Arrhenius equation involves the plotting of the natural logarithms of our rate constants versus the inverse of our temperatures. Okay, so let's get the inverse temperatures and the natural logarithm of rate constant. Okay, so if we plot these values over here, okay, we get this curve here, and we have our linear regression equation over here, all right? So since we want to determine our activation energy, okay, so recall again our Arrhenius equation, which is lnk is equal to negative EA over R, 1 over T, plus lna, right? So that means that the slope, our value over here, is this part here, okay? So our slope is equal to negative 12392. So that is equal to negative EA over R. Okay, so that means the activation energy. Okay, so note what is the units of the slope, by the way. Okay, so our natural logarithm of k, this is going to be unitless. Okay, so we're multiplying the slope by 1 over t and our temperatures in terms of Kelvin. So that means the units of our slope is actually in terms of Kelvin. All right. Okay, so EA, that is going to be equal to the slope times R. Okay, so that is 8.314 joules per mole Kelvin. Okay, so we can see here that our Kelvin cancels out, and our activation energy, when we convert this to kilojoules, okay, so 1 kilojoule, this is 1,000 joules, this is equal to positive 103 kilojoules per mole of the reaction. Okay, so this is the activation energy determined via the Arrhenius equation. Okay. So overall, now that we have a clearer picture of what happens during a chemical reaction, we can now look more closely at other more complex processes, okay? So the examples that we looked at were very simple ones that involved a single step, but it's usually the case that a reaction involves multiple steps to go from the reactants to the products, okay? So these steps can be described by the reaction mechanism, okay? So again, a reaction can occur in a series of elementary steps, which are reactions that occur through a single collision or transition state between the corresponding reactants involved. Okay, so as an example, say that we have reactants A and B colliding to form C and D, but D actually collides with another molecule of B to form the final product E. All right, so the net reaction in this case is A plus 2B yielding C plus E, all right? So note that we typically just know the net reaction right off the bat, and the net reaction does not indicate intermediates like species D over here, okay? But analysis of the reaction mechanism can show us what other species are actually involved in going from the reactants to the final products, right? Okay, so in analyzing reaction mechanisms, let's keep in mind several rules. Okay, so the first rule is that the sum of the elementary steps gives the overall reaction. Okay, so the second rule is that the slowest step in the mechanism constitutes the rate determining step. Okay, but note, however, that not all reaction mechanisms have a known slowest step or rate determining step. Okay, so later on we'll see how we could deal with those types of cases. And third, the overall rate law must be consistent with the observed rate law. Okay, so of course the proposed mechanism that we have has to be consistent with our empirical data. Okay, so we just have to make sure that it's consistent with the observed rate law. Okay, so before we proceed with anything, we have to make sure that we understand important things about elementary steps. Okay, an elementary reaction, recall, occurs directly as a collision between reacting species. Okay, so this means that the orders of each reactant in the rate law is actually equivalent to the stoichiometric coefficient. Okay, so it's only in the case in which we have single-step reactions can we immediately correlate the stoichiometric coefficients as the corresponding orders for each reactant. Okay, so we could rationalize this by thinking of the elementary reaction as a collision, right? So for example, we have A plus B yielding C, right? So this corresponds to a collision between reactants A and B to form product C, okay? So we know that the rate then is going to be proportional to the concentration of A, okay? So the greater the concentration of A, the greater the chance for an effective collision between A and B, okay? So the same thing goes for concentration B, okay? So the greater the concentration of B, there's a greater chance for an effective collision between A and B, okay? So putting these two things together, the rate is proportional to the concentration of A times the concentration of B. So instead of A reacting with another species B, say that it reacts with itself, okay? So it's colliding with itself, okay? So in this case, our reaction is 2A yielding C. So that means the rate of the reaction is going to be proportional to A twice, okay? So in other words, the rate is going to be proportional to A squared, okay? So that's why we could write the rate law for this elementary step as K times A squared. The order of the reaction with respect to reactant A is equivalent to the stoichiometric coefficient. Okay, so again, equating the stoichiometric coefficient to the order of the reaction only applies for elementary reaction, because we know that the elementary reaction corresponds to a direct collision or transition state between the reactants in the elementary reaction. Okay, so if we're now dealing with multi-step reactions, okay, for example, if we have a net reaction of A plus B yielding C, and we know that it involves two steps, okay, so we can say that the first step involves A plus A yielding D, and the second step involves D plus B yielding C to give us a net reaction of A plus B yielding C. The overall rate of the reaction will be dependent on the rates of the elementary steps, okay? So the rate for the first step here is given by K1 times the concentration of A squared, and the rate of the second step is given by K2 times the concentration of D times the concentration of B. All right, so there's two possible cases that can happen. Okay, so one is that the first step is the rate determining step, so meaning that it's the slowest step in these two elementary steps. Okay, so that means that the overall rate of the reaction is just going to be dependent on the rate of this slow step here. So the best analogy for using the rate determining step as our overall rate of reaction is given by this hourglass with multiple necks, okay? So the slow step is the one that has the thinnest sort of neck over here, whereas the fast step has the widest neck, okay? So we can see here that the flow of our sand through our hourglass is going to be dependent only on the slow step, okay? So the slow step is kind of like our bottleneck, okay? So it overall determines the rate of the entire process, okay? So we could say here that if step 1 is the rate determining step, the rate of the reaction is just K1 times A raised to 2, all right? So the second case is when things get a little bit more complicated. So case 2 is when a step other than the first step is the rate determining step. Okay, so this means that the second step over here is the slow step and the first step over here is the fast step. Okay, so using our hourglass analogy, okay, so that means that the bottleneck is our slow step over here. The overall rate of the reaction is now just going to be dependent on the rate of our second step over here, okay? So we could say that the rate of the reaction is equivalent to the rate of the slow step, okay? So that is K2 times the concentration of D times the concentration of B, all right? But the complication with this, however, is that the rate of the slow step involves a species that does not appear in our net reaction, okay? So this involves the concentration of an intermediate which is very hard to measure, okay? So it's very hard to determine the concentration of this intermediate. So ideally, rate laws should just be in terms of concentration of reactants. So there are two methods in order to express the concentration of an intermediate in terms of reactants. And the first of these methods is the so-called pre-equilibrium method, okay? So this assumes that the fast step already achieves equilibrium, okay? So in this particular case, that means our first step, which is our fast step, already achieves equilibrium, okay? So that means the reverse process occurs at a significant rate already, okay? So as we discussed earlier, we know that if a reaction has already achieved equilibrium, this means that the rate of the forward reaction is equal to the rate of the backward reaction, okay? So the rate of the forward reaction is expressed as K1 times A squared, and the rate of the backward reaction is given as the rate constant for the backward reaction, K negative 1 times the concentration of D. Alright, so we could actually solve for the concentration of D then, okay? So the concentration of D is just K1 times A squared over K negative 1. And we could now input this expression for D in terms of the concentration of A in our rate expression, okay? So we know that the rate of the entire reaction is equal to K2 times the concentration of D times the concentration of B. So just inputting this expression over here, we can now have our rate law as follows, okay? So simplifying this expression, we could write down the rate as the overall rate constant times the concentration of A squared times the concentration of B. Alright, so K can be expanded into the individual rate constant components, okay? So K is equal to K2 times K1 over K negative 1. Okay, so another important thing to note about equilibrium, by the way, now that we're in this topic, is that we could arrange this expression in the following way. So the concentration of D over the concentration of A squared is equal to the rate constant of the forward over the rate constant of the backward reaction, okay? So note that this ratio over here, this is pretty much just equal to the equilibrium constant expression, okay? So our equilibrium constant, we could also think of it as a ratio of the rate constants of the forward and the reverse reactions. Okay, so the alternative method for expressing the concentration of an intermediate in terms of reactant is the steady state approximation. Okay, so the steady state approximation assumes that a steady state is achieved for the intermediates. Okay, so this means that the concentration of intermediate remains constant because as soon as it's being produced in the reaction, it's immediately being consumed. So that means that the rate of appearance of the intermediate minus the rate of disappearance is just equal to 0. Okay, so the steady state approximation is actually more applicable in use compared to the pre-equilibrium method because the steady state approximation can also be used for cases in which we don't know what the rate determining step is. Okay, so for our particular example, let's try to apply the steady state approximation. Okay, so the intermediate in this case is D, right? So that means we could express the change in concentration of D with time. Okay, so we know this to be equal to 0. Okay, so let's look for the rate of appearance. Okay, so let's look for reactions in which D appears. So that is the forward reaction of our first reaction over here. So that is K1 times A squared. Okay, so it doesn't really appear in any other reaction. Okay, so we need to subtract the rate of disappearance. Okay, so it's being consumed in the reverse of the first reaction, so that is K negative 1 times the concentration of D, and it's also being consumed in the second reaction over here. Okay, so that is K2 times the concentration of D times the concentration of B. Okay, so we could solve for an expression for D then. Okay, so rearranging this expression, we have K1 times the concentration of A squared is equal to K negative 1 D plus K2 concentration of D times the concentration of B. Alright, so solving for D, this gives us K1 times the concentration of A squared over K negative 1 plus K2B. Alright, so here we have our expression for the concentration of D. Okay, so we know that the rate of the reaction is given as the concentration of D times the concentration of B times the rate constant of the second reaction. Okay, so inputting our expression for the concentration of D over here, we now have our rate of reaction expressed as K2 times K1 times the concentration of A squared over K negative 1 plus K2 times B times the concentration of B. Okay, so it looks really complicated right now, right? But from what we know about our reactions over here, we know that this is the fast step, right? And this is the slow step. So this tells us something about the magnitudes of our rate constants, okay? So in the denominator over here, we have a term of K2 times B, and we also have K negative 1, okay? But since we know that the first step is the fast step, okay, so this tells us that K negative 1, this is much greater than K2. Alright, so this means that the denominator over here, this can simplify out with some approximation, okay? So the value of the denominator is mostly dominated by this value over here, K negative 1. K2 times the concentration of B, this can be considered to be negligible, okay? So that means the rate of our reaction can be simplified as K2 times K1 times the concentration of A squared times the concentration of B over K negative 1, okay? So actually this equation over here, this is equivalent to the expression that we got when using the pre-equilibrium method, okay? But the steady state approximation is probably more useful since it's more applicable to other cases, okay? So there are some cases where we don't know which step is the rate determining step. Okay, so the steady state approximation does not make any assumptions about which step is the fastest step. Okay, so note that we only made that assumption in the final analysis over here. Okay, but the pre-equilibrium method needs to have an assumption of which is the rate determining step. But in this particular case over here, we just assume that the concentration of intermediate is at a steady state. Okay, so later on we'll see how we could use a steady state approximation to analyze more complex reactions. Okay, but before we proceed to our special mechanisms, however, let's just get a little bit of practice with the steady state approximation. Okay, so we're given this mechanism over here and we're tasked to determine the rate law. Okay, so over here we're given that the rate determining step is this second reaction over here. Okay, so we could base the rate of the reaction on this rate determining step. Okay, but before anything, let's try to get the net reaction so we know what we're dealing with. Okay, so we can see here that a bunch of things can cancel out upon adding all our elementary steps. Okay, so this cancels out, this cancels out, this cancels out, this cancels out. So we're left with hypochlorite reacting with iodine to form hypoiodide plus chloride. Okay, so these are our reactants. Okay, so hopefully we'll just see these species in our rate law. Okay, so we could express the rate of our reaction as the rate of step 2, which is equal to K2 times the concentration of iodide times the concentration of hypochloric acid. Okay, so hypochloric acid, this is an intermediate. Okay, so we could use the steady state approximation, solve for the concentration of hypochloric acid in terms of our other species. Okay, so using the steady state approximation, we know that the concentration of this intermediate is constant with time. Okay, so that means the rate of its appearance minus the rate of its disappearance is equal to 0. Okay, so let's look for cases in which it appears. Okay, so it appears in the first reaction, the forward reaction here. Okay, so we have K1 times hypochlorite. Okay, so note that water here acts as a solvent, so its concentration is very large, so we no longer include it in the rate expressions over here. Okay, so let's check out other places. So this is the only place where it appears. Okay, so it's being consumed in the reverse of the first reaction, so that is negative K negative 1 times the concentration of HOCl times the concentration of hydroxide. and it's also being consumed in the second step. Okay, so this is minus K2 times the concentration of iodide times the concentration of HOCl. Okay, so solving for HOCl, this will be K1 times the concentration of hypochlorite divided by K1 times the concentration of hydroxide plus K2 times the concentration of iodide. Alright, so inputting this expression into our expression for rate, okay, so rate, this is equal to K2 times the concentration of iodide times K1 times the concentration of hypochlorite over K1 times the concentration of hydroxide plus K2 times the concentration of iodide. All right? So you can make an approximation on the value of this denominator over here. So since the first reaction is a fast reaction, this implies that K negative 1, this is much, much greater than K2, okay? So that means that this term over here that contains K negative 1 dominates the denominator expression, okay? So we could say that this expression over here, K2 times the concentration of iodide, becomes negligible or 0, okay? So we could approximate our rate expression as K1 times K2 times the concentration of iodide times the concentration of hypochlorite over K negative 1 times the concentration of hydroxide. Okay, so actually this becomes our rate law over here. Okay, so note that the concentration of hydroxide, which doesn't seem to appear in our net reaction, doesn't cancel out in our rate law. Okay, so we could see that the rate of the reaction shows a dependence on the concentration of hydroxide. All right, since hydroxide appears in our rate law, we can see that the rate of the reaction is highly dependent on pH conditions. Okay, so this is a special case in which the rate law includes other species besides the reactants. Okay, so just be aware that this type of rate law is possible. Okay. Okay, so now let's try to look at different types of reactions in which we don't make an assumption about which step in the mechanism is the rate determining step. Okay, so the first of our special mechanisms is the unimolecular reaction, or the one reactant type of reaction. Okay, so the question is, what type of collisions can we have when we just have one reactant involved? And how can we describe this reaction with elementary reactions? Okay, and recall again that we dealt with this type of reaction with our integrated rate expressions, and we considered cases in which it might be first order or second order. Okay, so let's look at conditions in which this type of reaction might change in reaction order depending on the conditions. Okay, so the mechanism for unimolecular reactions was proposed by Lindemann, and it involves several steps. Okay, so the first step is the activation step, in which two reactants A collide with one another, and the collision results in a transfer of kinetic energy from one reactant to the other. Okay, so in effect, one reactant, A star, becomes more energetic than the other one, so it becomes activated, and it's quite energetic so that it could easily form the transition state. Okay, on the other hand, we also have the deactivation step, which is just the reverse of the activation step. Okay, so it's also possible that other non-activated reactants will collide with A star, leading to the transfer of its kinetic energy and making it less energetic. Okay, but if A star doesn't get deactivated, on the other hand, the next step is the breakdown of A star to form products. Okay, so when we add all these reactions together, we just get A yielding products, okay? So note that we don't really have an established rate determining step in this mechanism, but we can derive a general expression for the rate of the reaction using the definition of reaction rate as well as the steady state approximation, okay? So we know that the rate of the reaction can be expressed as the rate of appearance of product, and that is based on the last step over here, okay? So our reaction rate is just going to be equal to K2 times the concentration of A star, okay? A star, however, this is an intermediate, but we can express its concentration in terms of A with use of the steady state approximation, all right? Okay, so let's write down the change in concentration of A star with respect to time, okay? So that is equal to 0. So let's write down the rate of its appearance. Okay, so it appears in the first reaction, the forward reaction. Okay, so we have K1 times the concentration of A squared. Okay, and it gets consumed in the next two reactions. So we have minus K negative 1 times A star times A minus K2 times the concentration of A star. All right. Okay, so if we solve for A star now, okay, so A star, this is going to be equal to K1 times the concentration of A squared over K negative 1 times the concentration of A plus K2. All right. Okay, so if we input this expression now in our expression for rate, we now have rate of the reaction is equal to K2 times K1 times the concentration of A squared over K negative 1 times the concentration of A plus K2. All right, so actually we have this really complicated looking rate law, okay, but this rate law can simplify based on the different conditions of our system, okay? So let's check out what happens when, for example, we have a high concentration of A, all right? Okay, so we'll mainly be looking at how we could simplify the denominator over here, okay? So if we have a high concentration of A, this means that K negative 1 A is expected to be much greater than K2, all right? So the implications of this statement over here is that the rate of the activation at high concentrations of A is faster than product formation over here, okay? So this makes sense intuitively because if we have a high concentration of A, it's more likely that an energetic reactant A is going to be colliding with a lot of other reactants, right? Okay, so it's expected that the rate of the activation is going to be higher, okay? So once we have this statement over here, we could simplify our denominator, okay? So that means our denominator, which is K negative 1A plus K2, this simplifies to just K negative 1A. All right. Okay, so we could input this into our expression. Okay, so our rate can be approximated as K2, K1 times the concentration of A squared over K negative 1 times the concentration of A. So this simplifies to, okay, so we have rate is equal to K1, K2 over K negative 1 times the concentration of A. All right. So if we have high concentration of A, this means that the order of our reaction appears to be first order, okay? So in effect, it looks like the rate determining step is this step over here, okay? So the reaction is overall dependent on the decomposition of our activated species to form our products, okay? So we could also do a similar analysis at low concentrations of A, all right? Okay, so again, we'll be looking at the effect of the concentration of A on the denominator over here. Okay, so if you have very low concentrations of A, okay, so this could mean that K negative 1 times the concentration of A is going to be much less than K2, okay? All right, so making a similar analysis, the implications of this is that the rate of the activation is actually pretty slow, okay? So at low concentrations of A, as soon as we form an activated complex, it's not likely for it to start colliding with any other reactant because, again, we have a very low concentration of A anyway, okay? So again, there's going to be fewer possible collisions for deactivation, okay? So overall, it's likely that as soon as we form an activated species, it could easily break down to form products, okay? Okay, so ultimately we could simplify our denominator over here. So since K negative 1A is much, much less than K2, okay, so that means our denominator expression over here, this simplifies to just K2, okay? So our rate can just be written as K2 times K1 times the concentration of A squared over K2. So this further simplifies to rate is equal to K1 times the concentration of A squared. All right. Okay, so this over here, this is actually equivalent to the rate of the first step, right? Okay, so this tells us that at low concentrations of A, okay, so the rate determining step is the activation step, all right? Okay, so in our particular analysis of our unimolecular reaction, we made no initial assumption as to which step is the rate determining step, but after deriving this general expression over here for the rate law using our steady state approximation, okay, so we were able to get an expression and even analyze what the order of our reaction will be based on different conditions, okay? So the next special mechanism that we'll be analyzing is radical chain mechanisms. Okay, so you're probably familiar with radical chain mechanisms from your study in organic chemistry, and you know that these types of reactions are very, very fast reactions because they involve radical species, which are highly reactive species. Okay, so the example of a radical chain mechanism that we'll be discussing is the thermal decomposition of acetaldehyde. Okay, so this is described by the Rice-Hertzfeld mechanism. Okay, so the net reaction is as follows. Okay, so acetaldehyde is going to decompose to methane and carbon monoxide. Okay, so as with all other radical chain mechanisms, the mechanism starts with an initiation step. Okay, so this is the splitting of a species into two radical species. Okay, and then after initiation, we have our propagation step. Okay, so an example of a propagation step might be the reaction of a radical species with our reactant to form another radical species plus one of our desired products. And another possible propagation step is the reaction of the formed radical from the previous step to form another product and also reform another radical here. Okay, so these two steps are our propagation steps, and we could also have a termination step in which two radical species react together to form a byproduct. Okay, so all of these reactions occur very, very quickly because all of them involve radical species. Okay, so it's not very practical to say that any of these steps is a rate determining step. Okay, so we'll be using again our strategy of getting a general expression for the rate of our reaction based on the rate of appearance of one of our products. Okay, so in this case, let's use the rate of formation of methane. Okay, so we could see here that methane is being formed in our second step over here. Okay, so we could say that the rate of our reaction is going to be equivalent to the rate of formation of our methane, which is described by the second step over here. Okay, but of course, when we express the rate of our second reaction over here, we include an intermediate species, which we especially know to be very fleeting in existence. Okay, so we need to express this radical species in terms of other species. Okay, so we'll be using the steady state approximation again. Okay, so let's write down the steady state approximation for our methyl radical. Okay, so that is, okay, so its change in concentration is going to be equal to 0. Okay, so let's check out places where it appears. Okay, so it appears in the first step. So we have K1 times the concentration of acetaldehyde. Okay, so it also appears in the third step. Okay, so we have plus K3 times the acetaldehyde radical. Right, and then it gets consumed in the second and the fourth steps. Okay, so we have minus K2 times the concentration of methyl radical times the concentration of acetaldehyde minus the fourth step over here, so that is K4 times the concentration of methyl radical squared. All right. Okay, so note, however, that our expression for the steady state approximation for methyl radical also contains the expression for our other intermediate, the acetaldehyde radical. So it's also necessary to write out an expression for the rate of change of concentration for the acetaldehyde radical. Okay, so this is an intermediate, so its concentration change is just going to be equal to 0. Okay, so let's check out places in which our acetaldehyde radical appears. Okay, so it actually just appears in the second and the third reactions. Okay, so it appears in the second reaction, so we could write this as K2 times the concentration of methyl radical times the concentration of acetaldehyde, and it gets consumed in the third step. Okay, so we have minus K3 times the acetaldehyde radical. Okay, so overall we have two equations then. So let's call this equation 1, let's call this equation 2. Okay, so a nice method then that we could use to combine these equations is just to add them together. Okay, so we can note here that we have several terms that are similar, and if we add these two equations together, we could actually see that they're going to cancel out. Okay, so we have this negative K2 term over here, and we have this positive K2 term over here, and we have a positive K3 term, negative K3 term. So if we add these two equations together, note that they are both equal to 0. So we have 0 is equal to, okay, so this cancels out, this cancels out. Okay, so we end up having K1 times the concentration of acetaldehyde minus K4 times the methyl radical concentration. Okay, so using this equation now, we could solve for the concentration of our methyl radical. Okay, so that is going to be equal to K1 times the concentration of acetaldehyde over K4. All right. Okay, so let's just move on to the first slide for more space here. Okay, so again, we expressed our methyl radical as equal to the square root of K1 over K4 times the concentration of acetaldehyde raised to 1/2. Okay, so if we input this expression in the expression for our rate, okay, so our reaction rate, this is going to be equal to K2 times the square root of K1 over K4 times the concentration of acetaldehyde raised to 1/2 times the concentration of acetaldehyde. Okay, so this simplifies out to rate is equal to K2 times the square root of K1 over K4 times the concentration of acetaldehyde raised to 3/2. All right, so this is the overall rate law for our thermal decomposition of acetaldehyde. Okay, so note that we have an overall fractional order. Okay, so this is an example of a mechanism that might lead to this fractional order. Okay, all right, so overall, this will be the scope of our discussion. Okay, so we just discussed different special mechanisms and how we could derive an expression for the rate law. Okay, so again, we did a more general approach for determining the rate laws for these special mechanisms. Okay, so we didn't really assume any step to be the rate determining step initially, but we generally just got an expression for the rate of the reaction based on our definitions for rate. Okay, which in this case is the rate of appearance of product. Okay, and then we use the steady state approximation to derive expressions for the concentration of intermediates in terms of reactants. Okay, so overall, I'd also like to take this time to just thank you guys for tuning into our channel. Okay, so actually this will be the last video in our Introduction to Physical Chemistry lecture series. Okay, so In the future, we might have additional videos for more advanced topics, okay? So this video will serve as the last video for our basic introduction to physical chemistry. All right, thanks again.